Hello, everyone. Today we're going to go over section 3.1 over percents and applications. The language of financial mathematics is built around percent notation. And even though percent notation is used in many different common situations, misunderstanding what percents represent often leads some people to make decisions which they later regret. So, before we dive into the more complicated formulas used in finance, we will first review the percent problem and its uses. Recall that a percent problem is a statement either in the form part is percent of base or percent of base is part. We can solve a percent problem by translating the statement to an algebraic equation. Remember, even though percents look like numbers, they are not the same. When we translate percents into algebra, we need to convert from percent notation to either a fraction or a decimal. So when we're given a question such as 35 is 20% of what number, we can answer it by translating into a percent equation. The word is usually represents the equal sign, and of usually becomes multiplication. Our unknown, what number, can be represented by x. That leaves the percentage 20%, or written out numerically, 20 and the percent sign. Converting from a percent to a decimal, 20% means 20 over 100, which is 0.2. Converting from a percent to a decimal, we move the decimal place 2 to the left. So 20%, 1, 2 to the left becomes 0.2. Or you can use the fraction to get you there. But once we have that 20% is 0.2, we can write the statement as the equation 35 equals 0.2 times x. 35 is 20% of what number? It's a direct translation. Is becomes the equal sign, of becomes multiplication, what number becomes x. From here, we use algebra to solve the equation by dividing both sides by 0.2. 35 divided by 0.2 would be x, and 35 divided by 0.2 is 175. So 175 is x. We can follow a similar strategy for the question 42 is what percent of 30? Again, the word is usually represents the equal sign, and of usually becomes multiplication. Our unknown, what percent, can be represented by x. Putting everything together, we get the equation 42 equals x times 30. 42 is what percent of 30? Solving by dividing both sides by 30, 42 divided by 30 is 1.4. So we find that 1.4 equals x. However, this is a decimal value, and we pointed out earlier that the problem asks us for a percent. So to finish, we have to convert from decimal to percent by multiplying 100 and adding the percent sign. 1.4 times 100 is 140. Add that percent sign. Or you can just move the decimal point 2 spaces to the right. 1.4, move the decimal point 1, 2, and you would get 140%. If you need to keep track of which direction the the decimal point moves, then think of it alphabetically. In the alphabet, D comes before P. D is to the left of P. If you drew an arrow from D to P, you would be drawing the arrow to the right. If you were drawing an arrow from P to D, you'd be drawing that arrow to the left. So it's two spaces either to the left or to the right, depending on if you're going from decimal to percent, that's to the right, or percent to decimal, which would be to the left. In practice, percent problems are not usually presented in such clear language. In those cases, understanding the problem involves finding the percent problem that's hiding in its presentation. Example 1. In a survey of one neighborhood, they found that 64% of the neighborhood, or 176 households, subscribed to a satellite television service. How many households were surveyed in this neighborhood? So step 1, we want to understand the problem. Reading this situation carefully, we can see that this is a percent problem in disguise. We are told that 176 households is 64% of the neighborhood and asked to find the size of the neighborhood. So now that we have a percent problem, we should be able to solve it by translating to an equation and solving. So take a look at this. 176 is 64% of the unknown. 176 equals 0.64 times x. So again, we can abstract the percent problem as 176 is 64% of what number? Translating into algebra, is becomes equals, of becomes multiplication, the percent becomes a decimal. What number is x? We can solve this equation by dividing both sides by 0.64, which gives us the result 176 divided by 0.64, 275 equals x. So we have the result that x equals 275. In the language of the problem, that would mean that there were 275 households surveyed in the neighborhood. Before we are satisfied with this answer, we should look back at the situation and make sure that it makes sense. 275 households is on the large size of what might be called a neighborhood, but it's not unreasonable. And 176 households out of 275 using a satellite television service seems reasonable as well. With that, we can be satisfied that our conclusion that there are 275 households in this neighborhood is accurate. It's important to think about whether the result makes sense, as it could disqualify answers that are incorrect due to decimal errors. We got 275, but decimal errors could give us 2.75, 27.5, 2,750, etc. So thinking about the answer in the context of the problem would make us rule out these numbers. Let's talk about percent change now. In practice, we often use percents to measure the change, either increase or decrease, of a value over time. There are several mathematical approaches to solving percent change problems. One straightforward option is to think of a percent change as the distance from 100%. In this sense, a 30% decrease would be 100 decreased by 30, or 70%. Similarly, a 45% increase would be 100 increased by 45, or 145%. One important thing to remember about percent change is that it is always measured from the original value, whichever value happened first in time. This is important because percent increase and percent decrease are not inverses of each other. We demonstrate this with our next two examples. Example 2. What is 60 increased by 20%? Step 1 would be to understand the problem, and this is a percent increase problem, stated very simply. Let's devise a plan. We can rewrite a percent change problem as a basic percent problem. A percent increase means more than 100%. Once we have a basic percent problem, we'll be able to translate it into an equation and solve as we have done previously. So as we carry out the plan, we still have our original question: what is 60 increased by 20%? We're looking at increasing by 20%, so that would be the same as taking 120% of our starting value. Remember, a percent increase would be 100 plus whatever the percent we're increasing by is. In this case, it was 20, so 100 plus 20 would be 120%. So we rephrase the question as, what is 120% of 60? Next, translate this percent problem into an equation. What x is equals 120%, we would move the decimal 2 to the left, 1.2, of times, and then 60 would just be 60. We can solve x equals 1.2 times 60 by simply performing the indicated operation, which is multiplication. 1.2 times 60 is 72. So x equals 72. Looking back at our result, well, looking back at an abstract problem, there's not much to do. We double check that 72 makes sense as the result of increasing from 60, and it does, so we accept our result of 72. In the last example, we saw that increasing by 20% brought us to 72. In the next example, we look at what happens if we then try to decrease by the same 20%. So example 3, what is 72 decreased by 20%? The point of doing this is to show that we do not get 60. So increasing by 20% and then decreasing by 20% does not bring us back to the same value. But let's show this. Step 1, understand the problem. This is a percent decrease problem and stated very simply. Devise a plan. We can rewrite a percent change problem as a basic percent problem. A percent increase means more than 100, so a percent decrease means less than 100. Once we have a basic percent problem, we'll be able to translate it into an equation and solve as we have done previously. So if we're decreasing by 20%, that's 100 minus 20, or 80% of our starting value. So we rephrase the question, what is 80% of 72? Translate, what is x equals 80% of 0.8 times 72? And we can solve by performing the multiplication. 0.8 times 72 is 57.6. It was close to 60, but it was not 60. So again, this result may seem unexpected at first. We didn't end up back at 60 where we started. Percents and percent changes are taken from the starting value. In this case, our percent increase was taken from 60, while our percent decrease was taken from 72. 20% of 60 is 12, but 20% of 72 is 14.4. Both are 20% of something, but they are not the same. Once we let go of our preconception, we can see that 57.6 is a reasonable result when decreasing from 72. Let's have another example. In example 4, we're told that the population of Fairplace has increased from 52,100 to 57,310 over the past 8 years. What was the percent increase in population? So if we're understanding the problem correctly, we have that the starting population was 52,100, the ending population was 57,310, and we want to find the percent change. So let's devise our plan. We know that a percent change is the ratio of the amount of change to the initial amount. So first calculate the amount of change, then take the ratio of that to the initial amount. The fact that this occurs over an 8-year time period is irrelevant to the problem. So let's find the percent change first. Or sorry, the amount of the change first, which we would need to find the percent of the change. So 57,310 minus 52,100 means that there's been a change in the amount of 5,210. If we divide that by the initial amount, the starting point, 52,100, we get that 5210 divided by 52,100 is 0.1, or as a percentage, 10%. If you wanted to think of this in terms of a percent equation to solve instead of this ratio, the change is what percent of the initial amount. We found the change, 5210, is what percent, 5210 equals X, of the initial amount times 52,100. 5,210 equals X times 52,100. We would divide both sides by 52,100, giving us this same ratio. So that's where this ratio comes from, amount of change over initial amount. It comes from solving the equation. But amount of change over initial amount will always give us our percent increase or our percent decrease. Looking back at our result, the population of Fairplace has increased by 10% over the past 8 years. Now let's talk about some commercial applications of percents. A vibrant sign in the store's window boasts sale up to 30% off everything. Retail discounts are one of the more common ways that percents appear in our day-to-day lives. Mathematically, a percent-based discount is a percent decrease on the retail price of an item. So in example 5, we have that a thingamabob normally sells for $47. It is currently on sale at 15% off. What is the discounted price of the thingamabob? So understanding this problem correctly, we have that it is a percent discount problem. We need to find the result of 15% off of $47. We can solve percent discount problems by rephrasing them as percent decreases. This problem is really asking us, what is 47 decreased by 15%? A decrease of 15% is the same as taking 100 minus 15%, or 85% of the starting number. So what we're really looking for is what is 85% of 47. That would be 0.85 times 47, which is 39.95. That means that after the 15% discount, a thingamabob will now cost just $39.95. Example 6. A department store circular contains 2 coupons. One is for $20 off your purchase, and the other is for 20% off your purchase. How much would you need to spend to make the 20% off discount the better value? Now, if you understand percents very well, the answer to this problem is going to make complete sense. You might even be able to guess what the answer is just knowing what a percentage is. But let's do the math. We have two different options: the regular price discounted by $20 and the regular price discounted by 20%. The dollar amount, where which of these is larger switches, will be the point where they are equal to each other. So introduce a variable, write an equation, and solve for the unknown. Let X be the regular price of a purchase for which $20 off and 20% off gives the same sale price. $20 off of X can be written as X minus 20. 20% off of X is the same as 100% minus 20% or 80% of X, which can be written as 0.8 times X. Setting these equal to each other, X minus 20 equals 0.8X. Next, we'll subtract 0.8X from both sides, giving us X minus 0.8X minus 20 equals 0. Next, X minus 0.8X is the same as 1X minus 0.8X. So 1X minus 0.8X simplifies to 0.2X. We have 0.2X minus 20 equals 0. Next, this is a mistake here. It says subtract 20 from both sides, but algebra says to get rid of subtraction, we actually add. So this should say add 20 to both sides, which is what I've done anyway. 0.2x equals 20. 0 plus 20 is 20. Next, divide both sides by 0.2. 0.2x divided by 0.2 just leaves us with x. 20 divided by 0.2 gives us 100. So the price where the coupons are the same is 100. That means for any purchase of more than $100, the 20% off coupon will give a bigger discount. So again, a $100 purchase, both coupons would give you the same off. It would give you $20 off. 20% of 100 is 20. But that means that 20% of things over 100 is more than 20. So 20% off would be taking more than $20 off and would give you the bigger discount. So the answer to the question is you would need to spend more than $100. Moving on, we change our focus to the salesperson. In many sales positions, the salesperson is paid by commission, meaning they earn a small percentage of the total sales that they generate for the company. In example 7, we're told that Steven's sales job at Retail Outlet USA pays a 3% commission. If Steven was able to sell $925,000 worth of product in July, how much will Steven earn in commission for the month? Understanding this problem correctly, we would have that this situation is asking us to calculate a commission of 3% on $925,000 in sales. Devising a plan, we know that commission is a percentage of the total sales. So this problem is asking us to find 3% of 925,000. So let's carry out that plan. 3% of 925,000 is the same as 0.03 times 925,000, which is 27,750, meaning Stephen will earn $27,750 in commission in July. Wow. Everyone wants a job at Retail Outlet USA now. Let's talk about sales tax. The amount of sales tax charged on a purchase is simply determined as some percent of the total purchase. For example, if the sales tax rate in a city is 9.3%, how much sales tax will you pay on a $140 purchase? Well, the sales tax will be 9.3% of 140, which is 140 times 0.093, which is $13.02. Especially when asked to work backwards, it can be useful to model the total purchase, the retail cost plus the sales tax, as a percent increase. What do I mean by that? Well, let's take a look at example 8. Including a 7% sales tax, it cost $1,165.95 to purchase a new television. What was the retail price of the television before tax? Understanding this problem correctly would be knowing that the unknown retail price plus 7% in tax is $1,165.95. We can model this as a percent increase on our unknown. What starting value increased by 7% is 1,165.95. Well, an increase of 7% is 100% plus 7%, or 107% of the base value. So this problem can be rephrased as 107% of what number is 1,165.95. Writing that as an equation, 107% would be 1.07 of what number times x is equals 1165.95. Let's algebra it up. Get rid of multiplying by 1.07 by dividing by 1.07. And when we divide 1165.95 divided by 1.07, we get approximately 1,089.67. So rounded to the nearest cent, the television cost $1,089.67 before tax. Okay, now let's talk about income tax in the United States. Governments collect taxes to pay for the services they provide. In the United States, federal income taxes help fund the military, the Environmental Protection Agency, and thousands of other programs. Property taxes help fund schools. Gasoline taxes help pay for road improvements. While very few people enjoy paying taxes, they are necessary to pay for the services we all depend on. Taxes can be computed in a variety of ways, but are typically computed as a percentage of a sale, of one's income, or of one's assets. Income tax in the United States is often described as an incomprehensible black box, best left to the professionals. However, since the structure of taxes shapes most of the government's other policies, understanding how income tax works is an important part of being an informed citizen. The United States federal income tax on earned wages is an example of a marginal tax. People with a higher wage income pay a higher percent tax on different portions of their income, not on the entire amount equally. This is quite misunderstood over many people in the population. People think that when you're in a higher tax bracket, you're paying that higher amount on the entire wage. But that's simply not how it works. We have tax brackets, and this is how they work. Here is the 2018 federal income tax rate schedule for single individuals. You'll see that income levels are divided into 7 ranges called tax brackets, with a higher percentage rate charged against a higher income. So between $0 and $9,525, you're paying 10% of the amount over 0. But then when you get into this second tax bracket, $9,525 to $38,700, you're still just paying 10% of the $9,525. That would be $952.50. You're only paying 12% of the amount over $9,525. So you say you're in the 12% tax bracket, but you pay 10% on the amount that's in the 10% bracket and only 12% on the amount over that. Let's say you were in the 82,500 to 157,500 tax bracket, or the 24% tax bracket. Well, you're only paying 24% on the amount over 82,500. You're still paying 22% of the stuff that's in the 22% bracket, 12% on the stuff that's in the 12% bracket, and 10% of the stuff that's in the 10% bracket. So this table simplifies that calculation, but you're never paying 24% on everything. So let's look at this one more time. Let's consider a single person with a taxable income of $64,000. This person falls into the range of 38,700 to 82,500, which would be the 22% tax bracket. But they would pay $4,453.50 on the first $38,700 they earn. And then 22% only on that amount over 38,700, not 22% on everything. So to calculate how much they would pay, the 64,000 they make minus the 38,700 leaves us with 25,300. They pay 22% on the 25,300, 0.22 times 25,300 is 5,566. So in total taxes, they pay the They pay the $4,453.50 plus the 5,566, which would be a total of $10,019.50. Again, the most important thing to take away from this is that $10,000 in taxes is not 22% of the entire 64,000. It's 10% on the 10% stuff, 12% on the 12% stuff, and 22% on the rest of it. Many people misunderstand marginal tax systems because they miss the way that tax rates are only applied to the portion of a person's income that falls within that tax bracket. Some people believe incorrectly that moving to a higher tax rate can mean that a raise costs you money instead. So many people have heard of a story where someone says, I can't have that raise because it will put me into a higher tax bracket and actually cost me money. This is never, ever, ever the case. Now, maybe moving up above a certain level can cost you benefits of some sort that have a maximum amount that you can make and still be eligible. That is a reasonable consideration. But the taxes themselves will never cost you money by moving into a higher tax bracket. So to show why this is not correct, let's look at an example where a promotion moves someone from the 12% tax bracket to the 22% tax bracket. Brian has an annual salary of $50,000 and plans to take the standard deduction of $12,000. He is offered a promotion that comes with a $4,000 raise. How much more will Brian earn after taxes by taking this promotion? So we're looking at two different situations. Brian earns $50,000 and takes a $12,000 deduction, and Brian earns $50,000 plus $4,000 and takes a $12,000 deduction. We're asked to find how much more Brian will earn after taxes in the second situation. So we first need to know Brian's earning after taxes in both situations, which we can calculate using the tax rate schedule. We can then subtract these two values to find how much more he will earn in the second situation. So in the first situation, Brian earns $50,000 and takes a $12,000 deduction. If you've never done taxes before, if you've only dealt with TurboTax or you've taken it into a tax professional, the way the deduction works is it gets subtracted from your income and gives you a lesser taxable income. So that leaves him with $50,000 minus $12,000 or $38,000 in taxable income, which puts him at the top of the 12% tax bracket. 12% tax bracket ends at $38,700. He's at $38,000. So he'll pay $952.50 on the first $9,525. And then 12% of the remaining $38,000 minus $9,525 or $28,475 for a total of $952.50 plus 12% of $28,475, which works out to $4,369.50 in taxes. Subtracting that from his salary, Brian will earn $50,000 minus $43,069.50, or $45,630.50 after taxes. So this first situation, before Brian takes the pay raise, he's earning after taxes $45,630.50. Now let's look at the second situation. Let's look at after the raise. So instead of a salary of $50,000, he has a salary of $54,000. Again, takes the $12,000 deduction. $54,000 minus $12,000 is $42,000 in taxable income. This has moved him up into the 22% tax bracket. Now he'll pay $4,453.50 plus 22% of the amount over 38,700. So we have to find the amount over 38,700. 42,000 minus 38,700 is 3,300 for a total of $4,453.50 plus 22% of 3,300. He's only paying 22% on the final 3,300. And that works out to $5,179.50 in taxes. Subtracting that from his salary, Brian will earn $54,000 minus $5,179.50, or $48,820.50 after taxes. So subtracting the two situations, we get that after the raise and after taxes are taken into account, Brian has made an extra $3,190. He was not hurt by taking the raise and getting bumped into the next tax bracket, because you can't get hurt by moving into the next tax bracket. It's not mathematically possible with the way that taxes are actually calculated. So next time you hear someone say, "Oh, I can't take that raise, it'll bump me into the next tax bracket," explain that they are wrong and that they should take the raise. But again, if the consideration is, "Oh, I'll lose benefits if I go over a certain amount," that is a reasonable concern. But you'll never be penalized for a raise in terms of income tax. So in example 9, we found that if Brian takes the raise, he'll have $42,000 in taxable income. This would put him in the 22% tax bracket. But that's not his effective tax rate. Since he would only pay $5,179.50 in taxes, this is only 12.3% of the 42,000. So he has an effective tax rate of 12.3%. And that is this section. Next time I see you, we'll go ahead and do section 3.2.